In this video, we're going to be looking at another type of way to apply derivatives, and that's to look at how one rate of change might affect another rate of change. So we often have variables that are related, so if one changes, that's going to affect how the other one changes. Usually this is done over time. Okay, so most of our derivatives in this section are going to be with respect to time. And we call these problems related rates problems because the rates are related to each other. So let's just try an example. So suppose an oil leak spreads in a circular motion where the radius is increasing at 4 feet per minute. We want to know at what rate is the area changing when the radius is 2 feet. So what I normally do is think we need some variables. Okay, so here the radius is changing. So I'm going to call R to be the radius of the oil slick and the A to be the area. Okay, so now what we're given is we know that the area, or the radius is increasing at a constant rate of 4 feet per minute. So that's going to be dr dt. So it's the rate that the radius changes with respect to time. Okay, so remember the bottom part of these derivatives is telling us the variable that's respect to. So we know that this is increasing, so it's positive, and it's 4 feet per minute. Okay, so I put a little plus sign to emphasize the fact that it's positive. Okay, so I know it's positive because it's increasing. So when something increases, its derivative is positive. And what we want to find is we want the rate that the area is changing with respect to time when the radius is 2 feet. So this is at the time when r equals 2. Okay, so that's what we're looking for. So what we want to do, so I know the rate the radius is changing, and I also know how the area and the radius are related. Okay, so because the oil is a circle, so it's spreading in a circular fashion, I know that the area of the oil should be equal to pi times the radius squared, right? That's the area for a circle. So what we're going to do is we're going to differentiate implicitly. So we differentiate this equation. So this equation relates A and R. If we differentiate with respect to t on both sides, then we're going to have an equation that relates the rates. Okay, so that's what we're looking for. So we're going to do d by dt of both sides. Okay, so if I take the derivative of a with respect to t, the outer derivative is 1, the inner derivative is dA dt. Okay, and then the derivative of pi r squared, so the outer derivative is 2 pi r, so bring the 2 down and then reduce by 1 the exponent. And then I have to multiply by dr dt. Okay, so now I have an equation that gives dA dt in terms of r and dr dt. And I actually know both of those quantities. So dA dt, when r is equal to 2, is going to be 2 pi times 2 times dr dt, which we know is 4. Okay, so this is going to be 16 pi. Okay, and it's positive, so that means that the area of the oil is increasing at a rate of 16 pi, and then the units here, the units for the radius are in feet, so area is going to be in feet squared. And it's over time, and time was in minutes, so again, it's per minute. So the area is increasing at a rate of 16 pi feet squared per minute. Okay, so that's the idea of these problems. So let's just talk about the method we just used. So as normal, I'm going to encourage you to read the problem carefully. So it's useful to think about what is known or given, and what you want to find. Okay, sometimes a sketch can be helpful. I could have done a sketch above, but it would have just been a circle with a radius, so I didn't think we really needed that, but sometimes it can be useful. Okay, so then what we want to do is we want to write an equation, or find an equation, that relates, is relating the variables that you either have or want rates of. Okay, now what we're going to do is differentiate this equation. Okay, usually implicitly with respect to time. Okay, so we're often going to be using the d by dt, and we're gonna, each of the variables is changing over time. So like r, maybe I should go back up here, r, we should really think of as r of t, because it's changing with respect to time, and same with the area. So there's hidden t's in those variables. Okay, so we differentiate this, and then we are going to solve for the required rate and plug in known quantities. So you can't plug in things too early, or your derivatives will go to 0. Okay, so you have to take the derivative first before you plug in, unless they're constants always. If things are changing, you don't want to plug in the value that they're at any time until after you've done the derivative. Okay, so that's the idea. Now, to tell these problems apart from the, say, optimizing word problems that we just looked at, it's not too difficult usually, because the optimizing ones always say the words minimum or maximum, right? You're looking to optimize something. Whereas here, they always give you a rate and ask for a rate of some kind. Okay, so normally you're going to see the word rate of change, the words rate of change a lot. So let's see another example. Suppose a company is increasing production of candies at a rate of 50 cases per day. All cases produced can be sold, and the daily demand function is given by this, where Q is the number of cases produced and P is the price in dollars. We want the rate of change of the revenue with respect to time. Okay, when the daily production is 200 cases. Okay, so we know the demand, okay, which is like the price, and we want the revenue. Okay, and so let's think about what we're given. So here it's nice because we're given all the variables. Okay, we have P, Q, and R, the revenue. So what is this 50 cases per day? So that's not dP dt, it's actually dQ dt. Okay, so we're given dQ dt, and it's increasing, so it's plus 50. Okay, and this is cases per day. Okay, and what we want is dR dt, the rate that the revenue is changing when we're producing 200 units, so 200 cases. So we want an equation that relates revenue with number of cases. So we know that revenue is going to be the number of cases times the price that we sell the cases. Okay, so it should be Q times P. And because I have this formula for P, I can just insert it. Because I know P in terms of Q, now I have an equation of R in terms of Q. So if I expand here, what we get is 50Q minus Q squared over 200. So now I have an equation relating R and Q. Okay, so the revenue is equal to this in terms of Q. So what I want to do is take the derivative of both sides with respect to T. So the derivative with respect to T of R is going to be equal to the derivative of respect to T of 50Q. Now I just want to note this Q squared over 200. It might be easier to write it as 1 over 200 times Q squared. So we're not tempted to use the quotient rule. Although you could use the quotient rule, you just don't have to. Okay, so so the derivative of R with respect to T, this is just dr dt. Okay, now here, each time I differentiate a Q, I'm going to have to multiply by dq dt. So the first part, I'm going to get a 50, and then I have to multiply by dq dt. In the second part, I have this 1 over 200. It's going to be times by the derivative of Q squared, so 2Q, and then times by dq dt. Okay, so that's my derivative. And now I can evaluate. So dr dt, when Q is equal to 200, should be 50 times dq dt is 50. Okay, so times 50 minus 1 over 200 times 2 times 200, also times 50. Okay, so these actually 200s cancel out here. So I get 2500 minus 100. So I'm going to get 2400. That's my answer. Now, what are the units on here? So the revenue is in dollars, and the time was over days. So this is dollars per day. So what we'd want to say here is that the revenue is increasing because it's positive at a rate of $2,400 per day when the production is at 200 cases. Okay, so this rate might change will change as the production changes. So at different levels of production, the rate will be changing at a different amount. Okay, let's try another one. Here's one where a picture will be useful. Okay, so I have a ladder that's 25 feet long, and it's leaning against the side of a house. Okay, so let's just draw my picture here. I'm assuming that it's flat ground. Okay, so here's my house. Okay, and then I have a ladder. Okay, so it looks something like this. Now the ladder is always 25 feet long, right? It's not changing. So I can say that this is just 25. Okay, it's not, nothing's happening there. Now, the ladder begins to slide away from the wall so that the base of the ladder moves away from the house at half a foot per second. So this side is sliding away at a rate of half or 0.5 feet per second. Okay, now as that happens, the top is going to slide down the house. Okay, so we want to know how fast it's sliding down. So we need some variables. So you want to give the variables to things that are changing. So the distance from the base of the ladder to the house, this is changing because the ladder is being pulled away from the bottom. Okay, so this is getting bigger. And the height of the ladder up the house, this is also getting smaller. Okay, so that's also changing. So those are what I'm going to call my variables. And notice that I get a right triangle shape here. Okay, that's going to help us come up with an equation. So what we're given, okay, the ladder is 25 feet, and we know that the rate that x is changing, right, the base, we know that the rate that this part is being pulled away at half a foot per second. So that means that dx dt, okay, so x is getting bigger. So dx dt is going to be plus 0.5. Okay, and that's feet per second. Okay, now what we want is how fast the top of the ladder is sliding down. So what we're looking for is dy dt. Okay, and it's when the top of the ladder is 7 feet from the ground. So this is when y equals 7. Okay, that's what we're looking for. So that means we want an equation that relates x and y. And I can think of one, because we have this triangle, we have Pythagoras' theorem. Okay, so we know that x squared plus y squared should equal 25 squared. Okay, that's Pythagoras. I think most people have this ingrained in their head. A squared plus b squared equals c squared, right, for a right triangle. So we're going to take this and we're going to differentiate with respect to t. Okay, so that means I'm going to have d by dt of x squared plus d by dt of y squared is equal to d by dt of 25 squared. Now I don't actually care what that number is because I know, oops, I'm running out of space here. I know that the derivative is going to go to 0. So I know that x squared derivative is 2x, and then I have to times by dx dt. Similarly, y squared has derivative 2y, and then I need to times by dy dt. And this derivative of 25 squared, because 25 is a constant, the length of the ladder is not changing ever, this is going to be 0. So if I solve for dy dt, I would move this over. It's going to be a negative, and then I have to divide by 2y, so the 2's are actually going to cancel out. So I'm going to have negative x times dx dt over y. I didn't write this very well. Okay, so that's my derivative. So then I notice that I have an x and a y and a dx dt. Okay, I know dx dt and I know y, but I don't know x. So what we need to do is we need to find x. I'm going to do it here. Okay, so when y equals 7, we know that it satisfies this equation. So that means that x should be the square root of 25 squared minus 7 squared. Okay, so if you compute that, you actually get that x is 24. Okay, so I can add that in here. X is 24. So when y equals 7, it has to be that, because of the ladder length, it has to be that x is 24 at that moment. Okay, so that means that dy dt, when y equals 7 and x is 24, is going to be negative 24 times 0.5 over 7. Okay, so this is actually negative 12 over 7, which is approximately negative 1.7. Okay, now this is feet per second. So the units are the same as they were for x because it's just the length changing. So the length is in feet and the time is in seconds. Now, what does it mean that it's negative? Does that make sense? So remember, when it's positive, it means that we put a derivative's positive when the derivative is increasing, or when the amount is increasing. Here, the y value, the height, as the ladder comes down, is getting smaller. So it makes sense that the derivative here is negative. So y gets smaller. Okay, so it does make sense that derivative is negative. So now we should just write our conclusion. So the top of the ladder is falling. Okay, so it's going down at a rate of 1.7 feet per second. Okay, when it is 7 feet from the ground. Okay, so notice that we didn't need to know how tall the house was or how high the ladder was initially. All is that at some point it reaches 7 feet. So presumably the house is higher than 7 feet. So those are a few examples of solving related rates problems.